Alright, so next issue is non-circular sections. Do you remember? So I emphasized you several times that the discussion that we are making is only for circular sections. So if you consider torsion problems for arbitrary cross sections, we have some problems called warping. Okay, because of that problem, it is very difficult to apply the torsional problems, torsional equations, torsional formula, and the way of calculating stress directly to arbitrary cross sections. Now let's talk about the issues found in non-circular sections subjected to the torsional moment. Okay. So before we talk about the torsion of thin walled tube, I'd like to discuss with you these slides first. Okay. So let's consider I-shaped section here. So if you have I-shaped sections, and then also channel sections, and then also the angle section here. So if you apply torsional moments, not like circular sections, we have very interesting behavior here. Let's say this straight line here, for example, let's say initially we have a straight line, and then let's apply the torsional moment. And what happens is, this edge. So if you apply torsional moment, this edge comes out, and then this edge, goes in. And then if you look at this part, and this edge, goes in, and this part comes out. Okay. So, if you look at the cross sections, we have the cross section is kind of distorted, and this distorted shape of cross section is called warping. So in 우리말 뒤틀림. Okay, 뒤틀림. And then because of this, we have the actual displacement u. What I mean, let's put the coordinate x here. So we have ux, non-zero ux. Then what happened in the circular section? In the case of circular section, the story is a little bit different. For example, so if you consider the strips, let's consider small, very small strips here, the combination of very small strips to the circular sections. Let's say there exists some warping here for these small strips. Okay, this is very natural, isn't it, right? But if you consider infinitely, thin strips, okay, infinitely thin strips, and the warping disappears in this limit theory. That's why in circular section we don't consider this warping. But if you consider arbitrary sections like I-shaped sections, or even for example rectangular section, box girders, okay, so we always have warping. That causes problems. We have secondary stress development. To prevent this warping, such kind of warping, what we do is, so we put the diaphragm. For example, let's consider this rectangular section is subject to torsional moment. Instead of this, the rectangular, keeping the rectangular section, so we put diaphragm here regularly, very strong diaphragm, to prevent this warping distortion. Okay, this is called a diaphragm. In 우리말 diaphragm. If you translate diaphragm, this is nothing but 횡격막이죠, 횡격막. Okay, 횡격막. And also even the I-shaped section, let's consider the I-shaped section. Even in this I-shaped section, we put a stiffener. Okay, so regularly we put stiffeners to prevent this warping. This is very essential. Okay, otherwise we have warping displacement. Do you understand? Okay, let's say our point is we assume that we put a set of a number of diaphragms to prevent warping. So let's consider a thin walled tube, okay, which is an arbitrary shape of cross sections. Okay, because this is not circular, it produces warping too. But let's assume that so we prevent warping displacement putting the diaphragms here. So let's consider a tubular sections, arbitrary tubular sections here. As I told you, because the problem is homologous, so which means the situation here is same as situation here, okay? So which means shear stress that we measure at this point is same as shear stress measured at this point. Now because of this logic, let's say if you have some shear stress tau b, okay, and then we must have same shear stress here, tau b. And then we can measure the another shear stress at these 2 points. By the same logic, we have tau c and tau c. The problem, make sure that this problem is homologous, okay? Then, okay, so let's consider this small segment. So as given in my lecture note, so we are here. Then I have tau b, and then because of, the conservation of momentum, so we must have same tau b here. But here, and then also if you look at bottom surface, we have different tau c. So tau b and tau c, okay? So let's check the force equilibrium. So if you check the force equilibrium, the horizontal direction, and then here FB is given by what? So FB is given by tau b times the thickness measured at point B. And then FC, I'm talking about here, right? So FC is equal to tau c and then T thickness measured at point C. So according to force equilibrium, what does it mean? So FB is equal to FC, which means if we plug in the expression of FB and FC here, tau b times thickness at that point is equal to shear stress at another point, TC. So please make sure that point B and point C, they are just arbitrary points, which means the shear stress times the shear stress caused by torsional moment times the thickness is what? Constant. Okay, constant. For this closed section, this is constant. This is very important consequence. So we'd like to define that constant using so-called shear flow. Okay, here we want to shear flow. I want to define the shear flow is shear stress times thickness. This is called shear flow. in 우리말 전단 흐름. Just direct translation. Okay, the unit of shear flow is force per unit distance. That is the unit because we multiply the shear stress to thickness. Okay, let's play with shear flow. Let's imagine a circular section here. Okay, and then if you imagine a small segment measured by ds, then there exists the shear flow. As I told you, the shear flow is constant. And then the force caused by shear stress over that distance is measured by the shear flow times the distance ds. Please make sure that the shear flow is a force per unit distance. That's why this force vector, the magnitude of force vector, is measured as shear flow times the distance ds, the length ds, what I mean. And then let's try to calculate the torsional moment produced by the shear flow. Okay, the force due to the shear flow is shear flow times the length ds, and then we need to calculate the arm length. The arm length is denoted by the radius r here. This is small torsional moment. So we need to integrate the small torsional moment over the entire path of the cross section. So we need to integrate. Okay. So make sure the shear flow was constant, isn't it, right? It was constant. That's why we can take out the shear flow in front of integration. That's why we have shear flow here. And then the integration becomes very simple. So we need to integrate the radius times ds over the entire perimeter. But I want to see the physical meaning of the radius times ds carefully. Okay, let's look at this. The radius times ds means what? What is it? This is a square of the area of this small triangle. That's why this integration, we don't have to calculate this integration, integration is nothing but 2 times of the enclosed area. Okay, for this thin wall tube, torsional moment can be easily calculated by what? The shear flow times 2 times cross-sectional area. Okay, then how do you calculate the shear stress? Okay, once we have torsional moment, then we can calculate the shear flow, dividing torsional moment by 2 times the area enclosed by the middle line of the cross section. Okay, and then we calculate the shear stress at a certain point by dividing the shear flow by the thickness at that point. Isn't it? Yeah, it's very easy, right? Do you have any questions regarding this discussion? Please, once again, please make sure that that discussion is valid only, in a condition that we have what? We have diaphragms to prevent development of warping displacement. This is really important. Next subject is stress concentration. Okay, we already discussed the issue of stress concentration in chapter 2. In actually loaded members, if you have any change in the cross sections, a rough change of cross section, then we have so-called stress concentration. That's a stress concentration is purely determined by geometric consideration in the case of linear elasticity. In torsional moment 2, then we have to calculate so-called stress concentration factor, and then you can refer to the handbook to find out the information of stress concentration. So the solution procedure is this. The first, you calculate the shear stress caused by the torsional moment. Once we have the shear stress, that shear stress is called nominal shear stress, so-called 공칭응력, nominal shear stress. Then we need to multiply the stress concentration factor to that of nominal the shear stress to calculate the actual maximum shear stress value. Okay, here that's what we are doing here. So we multiply the stress concentration factor to the nominal shear stress value to calculate the maximum shear stress. Okay, so do you have any questions here? So if you don't have questions here, I'd like to take another 10 minutes break, and then we'll move to the chapter for the beam problems. So let's take 10 minutes break.